a full-blown landfall. Most of the circulation now is over the eastern U.S. here in portions of Pennsylvania into southern New York. As it moves northward, as I was saying, these things tend on the right side of the circulation to produce basically tornadoes. I was in the middle of in hot pursuit showing you basically that being the case. And so I wanted to, so here we did from the SPC. I was just going to back up and show you today's reports in case you can't contain yourself. And again, Kelly and ZWAT, excuse me, Control X. If we zoom in on here, which I can't do, we do have a few more tornadoes today as it moved through basically portions just south of, mostly south of New Jersey at this point. I don't see much in the way of stuff in New Jersey today. Of course, I'm not sure how up to date the reports are. So that would be an issue. I will have to check later today to see whether or not any tornado reports, gang, in New Jersey. So, just wanted to touch on that one briefly there for storm reports. So a buddy of mine at the University of Oklahoma wrote a famous paper many years ago. His name is Bill McCall. This was back in probably before most of you were born. These are really kind of cool. It's basically the size of the circular Fujita scale tornadoes on here. This is again a 1991 article by Bill McCall or Eugene McCall. You can see his name basically up here. And so you're looking at a hodograph. Most of you guys know what a hodograph is. And so this one's been oriented relative to storm motion. And so Kelly and gang, so the storm, so all these are for all the tornadoes produced basically, if you read his caption, locations of all reported hurricane tornadoes from about a 40-year period, basically, really cool. And everything's been rotated in the coordinate frame with respect to hurricane motion, which is kind of nice. So no matter what way the hurricane's moving, the quadrants are the quadrants on here, which is kind of nice. It's a clever way to actually do this kind of thing. And I forget how to do a line on here. Hold on a second. Let me see how to do a straight line. Oh, Control Q. Okay, so let's do this. So really quickly, in case you haven't seen, so if you get everything aligned towards storm motion, A ship and gang and Steph and everybody else, and then this guy over here is going to be the right, basically front quadrant, basically, since the storm motion is in that direction. All right, so that's left, and over here then would be basically left front, right, etc., and then right rear over here, yada, 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 you get the point, right? So let me not belabor it. Let me clear all that mess off. And so a take home in the study, which is really interesting, is look at the cluster of storms basically concentrated, not exclusively, but a lot of these tornadoes basically are in that right front quadrant with respect to storm motion. And there's quite a bit of discussion as to why that is. I'll say basically that the ingredients, the buoyancy and shear in that quad tend to be the most favorable basically in that quadrant. And so there you have it. Anyway, so I wanted to point that out. And I did, Colin and gang, actually have take a look. So if we bring up Sharp Eye, I did bring up a sounding. You see this little spot here in New Jersey. This is from the rapid refresh. So it's not an observed sounding, but I'm just going to be sampling from the rapid refresh. I just kind of, let me get rid of this guy. So I just basically right here, it's KTLH. So it's a model sounding from a 1 hour rapid refresh forecast. And one of the cool things about these is the classic. Like I wanted to try to find something, folks, that was basically ZWAT and gang, was basically, and Robert and gang, and John, I wanted to find something that was going to be to the right of the center, right? Because that's a favorite quadrant. And sure enough, basically, it's a classic photograph, Tangelo, just a classic photograph. For those who don't know what photographs are, I'll just sort of briefly let you know. This is the center of the photograph, basically, and you just draw, if anybody's had my weather briefing class, you just basically, the tip of the photograph, basically, at each level traces out the shape of basically and gives you an idea of the wind magnitude and exact idea and wind direction with height. So that's a particular level right there. I could keep adding more back. This would be the surface wind. This would be somewhere. And the red line's the lowest 3 kilometers, if you remember, for those who have my class. So if I draw another arrow up here, you can actually see what's going on, which is kind of cool. The winds are turning basically clockwise with height, right, Mr. Panor? Classic. And one of the key features, and they're fairly strong winds. I mean, these winds are impressive. These are in knots, the radii. And so we're looking at essentially a radii here, almost, if I get rid of this again here for a second, it looks like the Dr. L, that the hodograph radii at that location from the sounding. That's almost, if we look at it here, this little radii right through here, control X, looks like the Dr. L anyway, that this guy drops down to almost 70 knots. So that's a pretty good, that's pretty respectable right above the surface there. So the wind speeds at the surface basically from the rapid refresh are less than 30 knots. Up here, they're 70 knots. That's 40 knots basically of wind speed and some directional changes in the boundary layer basically as part of the, and so these cells that are in this quadrant are experiencing a lot of directional shear and a lot of speed shear, and that is one of the ingredients basically of tropical cyclones spawn tornadoes. If we went back to our original figure, folks, and if I did that, Lindsay and gang, right, and Anna, you'd find out basically ultimately if I sample in a different location, I guess we could. Let's take a look at what the hodographs look like, say, in here. I'll just have some fun. And then I'm going to load that guy up. What the heck, I'll just wing it because I just wasn't sure what I wanted to do here. So if we take a look at this guy basically, and that should be good. So that's KDRG, and let's load that one up and see what we get. So this was by the way, just a beautiful wind profile. And so A-Ship, now that you're in Texas, you'll be very familiar with these kind of wind profiles.
Yep.
With height.
Yeah, welcome to the Texas party.
Yeah, so everything's bigger and better in Texas. So here's
what they said.
So I mean, take a look at this guy. So this photograph's really quite a bit different, kind of all over the place in the low levels of the atmosphere. It looks like, at least in that location, you've got basically northeast flow at the surface, essentially, and then coming around to basically easterly as you work your way up. And nowhere near, there's some funky stuff in here, but nowhere near the, look at the wind speeds, right? So Colin, check this out, right? So, and rest of the gang and Lindsay and folks and Danielle, I see you floating around on there also. I mean, if you see this, except for this little weird spike here in the model sounding, we're looking at most of the winds for a good chunk of the lower portion near the surface are all under 30 knots. And outside of this one, we're nowhere near 70 knots. So again, it's no accident that this right front quadrant, if you think about the flow in that quadrant and you start doing stuff that Professor Split did with you guys, some of you guys in synoptics classes years ago, part of this issue is wrapped in the storm relative vectors. And so that's back to your Physics 101 class. If you're in the right front quadrant, you're in a quadrant where the winds, basically the circulation of the system is in the same direction as the motion, right? And so hint, hint, that's a big player there. So I did want to touch on that. And there is a lot written in the literature on that aspect of tropical cyclone produced tornadoes, a bunch. So, okay, so Dr. L will shut up there. And a couple of other comments basically that are also cool about the landfalling tropical cyclone. And so let's go back. I thought the discussion from the Hurricane Center was kind of fun as well. Of course, I have to find that discussion somewhere. And then, you know, I can see my organized desktop, what's new. And then, oh, there it is. It's in the first box. Don't say it, John.
First tab.
Yeah, of course, it's always the first tab. Josie, hi.
It's always the last tab.
It's always the last tab, right? All right, there's got to be a good joke there. Anyway, so I like the discussion. So the 11A discussion about Isaias discussion this morning, anyway, from the Hurricane Center, which I thought was interesting, and Z Watt, you'll probably find that interesting as well. And rest of the gang is the discussion. They're looking at, you know, they're not having recon. We're looking at the Doppler radar data. So I haven't shown you the radial velocity. So unless I get super distracted, that's my plan next. So somebody can catch me if I float somewhere else. Anyway, if you look at the Doppler radar data, and this is what they're looking at the Hurricane Center at Cadix. So this was basically south of the radar that I was showing you. This is, anyway, this morning they were looking at, what were they looking at? Well, kind of interesting stuff. They're looking at basically 70 to 80 knot radial winds, basically between about 4,000 and 7,000 feet over the ocean, just offshore, basically the Delmarva Peninsula, basically, and the Delaware, so DOX, excuse me, the DOX radar is in Delaware. The DIX radar is the one I was looking at with you guys, basically. What I like about their discussion, so for the neophyte out there, what I like about, I think is cool about their discussion, folks, is that they're talking about, what is this? Which would normally correspond to 65, 70 knot winds at the surface. Man, this is such a big issue. So here's what they're trying to do, guys. They're trying to basically, the radar, right? When you look at, when you're a radar, so let's see if Dr. Ill can, so here's Dr. Ill's attempt at a radar, basically. And so the radar is basically looking, and I had a figure for the radar, but I just probably won't spend any time on it. The radar is looking basically on a, it looks like basically on a tilt angle, sorry, it should be a straight beam. Anyway, I could have drawn a straight line, but I didn't. Control X. So it's looking at a tilt. So it's above the surface. It's not seeing surface winds. Even in close to the radar, you're still above the surface, right? So where do we live? We live near the surface. We need 10-meter winds, right? That's the winds that matter, generally speaking, near the surface, within about 30 to 50 feet of the surface. That's our lives, basically, for the most part. And so there's half science and half art to get the winds, basically, either from recon outside of dropsondes, anyway, they go all the way down to the surface. Trying to get estimates of surface winds, they use a step frequency microwave radiometer, the SFMR, of course, which looks at agitated waves over the water. But what's blowing in from the water to the land and how to bring that down to the surface is not a trivial matter. So what I really like is normally correspond to this guy here, but here's the how, here's the but. Right? You always like the buts, but these velocity values have been co-located with only 15 to 25 dBz reflectivity echoes. So imagine a classic wind profile in the atmosphere going up like this with winds increasing with height, peaking at some level as you get higher up in a hurricane. So this way basically is your vertical. So this is Z. So the idea in a hurricane, and I guess I'll pop, I should show you this since I actually loaded it. So hold on a second. What did I do with it? I don't know. Who knows? I've got obviously so much stuff loaded on here. What happened to that? So I do have, so there's the radial. All right, hold on a second. So let's do this. So, all right, so I'll be show you the classic. So I just wanted to show you really quickly, Control X, what the heck. So you start looking at wind profiles and a tropical cyclone, right? And here it is. I have it shoved off to the side here. So in this case here, you're looking at, oops, right there, good. And then you're looking at, let's see, Control S. This is height on this axis here. So in our tropical cyclone, actually, right above the friction layer, you have maximum winds. This is very different than mid-latitude cyclones where winds increase with height. This is a sort of classic hurricane wind profile with height. So this might be, oh, I don't know, this peak level winds might be around, let's just guess, I'll say around 850 millibars. And the question is, how do you get these peak winds or these higher winds? They come down in gusts to the surface. So the rain bands actually are really fascinating. They actually drag down the high moment. They're going up through the shear layer, right? So you end up basically with convection developing, right? Thunderstorms develop. There's Dr. L's little quick little thunderstorm. And then you have rainfall down through this layer, and it drags all that high momentum air down to the surface. That's why the winds get really high as these squalls pass. This is fantastic. And so here's the point I thought would help with the Hurricane Center discussion this morning is when you go back and look at this basically, which I think is interesting, and that is the, however, these velocity values have been co-located only with very weak, very low reflectivity values, right? So you're not pulling a lot of momentum. I'm reading in between the lines here because they're not interpreting for you guys. But what's going on ultimately in the discussion is that there's not a lot of water loading because there's not a lot of reflectivity. So there's not a lot of momentum transfer down from the level above where you have less friction, where the winds peak in the hurricane boundary layer, okay? And so they're back, so they're less, so the typical way, the typical ratios, they use ratios of wind speeds basically at the peak level, somewhere around 800 millibars or 850, as I was saying, maybe 750, depending on the storm. And so they use ratios basically, they use ratios to bring these winds down to the surface. And so the typical 85% reduction from that level likely don't apply. It would be an overestimate of the surface. Of course, you could always look at the surface laws to answer that question. I guarantee you that is the case, right? Anyway, so they're back off on that and saying basically sustained have been reported winds. So it's a great example basically on bringing winds down from aloft, right? And they're trying to use all the data they have without recon locally to get an idea of what basically of those peak winds that are being seen by the radar, you know, what's going to make it down to the surface. And there are other factors actually they haven't even mentioned here, but it turns out, interestingly enough, that the atmospheric stability matters as well. So if the atmosphere is more unstable, the winds tend to mix, those higher winds will tend to mix down more readily closer to the surface. In cases where the atmosphere is more stable, that would be less so, less mixing. So these things that Hurricane Center have to take into account. I thought it was kind of cool. It shows up in their discussion. So way cool. All right, you guys okay with that? Kind of neat, thumbs up, maybe. All right, not bad.
Yes.
All right, great.
Yeah.
Thanks.
Yeah. Or today, I was outside in a tropical storm. Yeah, and then and I did a live video of something.
Oh, you got a video.
Yeah. Video.
What's that one, John?
So John, you're in Maryland, correct?
Yes.
What?
Yeah.
John's at ground zero.
All
Yeah.
right.
Did you take any obs?
I was reading it, and it was 35 miles per hour.
So you're flirting with tropical sustained winds. Do you have a Kestrel, a handheld or something?
Yes. Yep.
Okay, very nice. Well, we've got our own Weather Channel reporter here then. Awesome. Yeah,
He's probably
John
better
is,
than the Weather Channel.
yeah,
More
yeah, thank
reliable.
you. I would say. And the other thing, he's got more experience too, because he's been out with us several times with the LiDAR, correct?
Yes. Mm-hmm.
Yeah, he's been a big help. We could have used your help this past weekend, trust me.
Yes.
Yeah, so, and he's been a big help. All right, so so I want to go back to some data. Why not, right? So that's why you guys are paying the big bucks. And so let's see here. Oh yeah, today's a freebie. What the heck? All right, so anyway, just kidding. Let me.
That's why we paid the big bucks how many years ago?
Right.
Right, and you're still collecting. Thank you. Which is important. Trust me, I appreciate it, even if I didn't always show it, right? All right, so anyway, so back to this. So this was the radar view, and I've been sort of looking at it all day. And let me, I just gotta move you guys out of the way for a second, off to the side, no offense. So let me zoom in here, it's kind of pretty, and I'll take this guy out. It just doesn't even want to do that. All right, so what I want to do is switch to radio velocity. And back up. I've lost a lot of my information as I move in here. Let's see, because it's stepped forward, I've kind of, this is kind of cool though. I just wanted to show you a couple of things. So this is the WSR 88D data basically out of the, at a KDIX basically in central New Jersey. So here we are, and you're looking at radial velocity, which is really awesome. And just to remind you what we're up to here, I can close this window here. I should have the, I just wanted to show you, if you look at the sort of beaming. So this is essentially height on the y-axis and range. So you're gonna be, I'll show you some range gates in a minute. And so for a ½ degree radar tilt, the beam is not a straight beam in this linear mapping here. It turns out, those who've had my remote sensing class, we talked quite a bit about why this is. The Earth's curvature plays a role here. And also the electromagnetic propagation through the atmosphere also matters as well. And so the beams curve away from the Earth's surface with distance and in a way that's non-linear, in a parabolic way. And so if you guys take a quick look, Tangelo and Kelly and gang, and you can actually see for a 1/2 degree tilt, basically, then we are what appears to be, oh my gosh, that's so crazy. Never mind, it just popped open another window. I have multiple commands going on, so where did it go now? I lost. Oh, somebody help me, right? I don't even know where that went. I was hoping to, let's see here. Now what did I do with it? It's disappeared. I have too much stuff open. Hold on a second. I did want to show you this. So I'll just take a second out, basically. Take a second over here. Move this over. Where did it go? I lost it. Oh, Dr. L's lost it all right. That's a metaphor. Anyway, let's see here. So if I talk like that on airship, I would probably get it. I would probably be a lot of trouble.
You know, it happens.
This is why I'm not an on-air meteorologist. So I don't know what happened to my, let me plug this one back up. Let me do file, let me do open recent. I think it closed it. There we go. So I'm back. So let's try this again. I don't want to make it full screen on you guys. I was just trying to write on this thing, and I think I'll just leave it to the regular. So at 100 kilometers, you can see here, Kelly and gang, about 100 kilometers, we're up about, it looks like, you know, that's not a bad estimate, right? It looks like we're, you know, at 100 kilometers away from the radar for a 1/2 degree tilt, for this tilt, we're up about, it looks at least what appears to me a couple of kilometers up, okay, off the ground, right? As far as the beam height goes, you know, 1 to 2 kilometers up, and that matters. Why does that matter? Because I can come back to my IDV here in a second. And so let me bring it back up. And minus that, so I get for having too many windows open. And so here I come back to the radial velocity field. And it's a little messy, but it's kind of cool. And so I just wanted to show you guys a couple of things here. And let me kill that guy. So, so a couple of features of interest, and I could put this in motion. And then let it go through. So you can see this banded feature. So where you have reflect, you need targets. You have to have targets. So, let me go back and forth here. I'm going to pivot back and forth. So let me get rid of, so where you have the reflectivity, got it? You got the, where you have raindrops, basically, in return, you have radial velocity. Now, it's not just raindrops. You can get radial velocity from other targets, from insects, all sorts of things. But clearly, you can see, folks, here a nice, right, Mr. Bishop, some nice correlation between where the radial velocity data is coming in and where the return is, we're coming in from, and reflectivity is concerned. Now, one of the cool things is if Dr. L can zoom in here and move you guys around. So let me just put you right there for a second, come back down. So one of the perils of using basically real data is that you, without it being processed or quality controlled, is this problem. So there is, if you've noticed up on the axis up here, you have basically -80 to +80 knots showing up in beautiful colors. So +80 is this nice little pink guy here. -80 is this nice black one. What is -80? Well, the radar basically is right here. All right, so that's the radar essentially, and it's scanning 360, all right? And so what do these colors mean to the layperson? Well, I'm going to tell you, hopefully. So essentially, these warmer colors essentially are basically motion. What have I got here? Should be motion away from the radar. So let me go ahead and draw these arrows. So these have a radial velocity component away from the radar, and the cooler colors basically have a motion toward the radar in this region here, right? So that's important, all right? And so the key here, of course, one of the features you want to find on these diagrams is the zero line. In this case, that's this nice sort of approximately sort of this boundary right here, right? So that's where you're shifting signs from data that wherever the direction the radar is looking, from flow towards the radar to flow away from the radar, okay? How do we know that? Because if the radar basically is looking, essentially, let me just show you, if the radar data, if the radar is actually looking in this direction here, right? at the surface, it's seeing zero flow, which means the flow is cross beam, right? Perpendicular to the radar. If the radar is looking this way, it's also seeing zero flow. So as it rotates 180 degrees, folks, basically it crosses that zero line where basically the flow is perpendicular to the radar beam, okay? And on this side of it, it is basically, now that I did that, on this side of it, basically it's away from the radar, and this side is toward the radar. Now, what do I want to show you? Well, here's a funky thing. Check this out. What's going on here? Pay attention to your data, folks. What is going on there? That's funky. Look at this one for a second. OMG. So we talk about this definitely a lot in remote sensing, basically, folks. So what is going on here? That just does, that's really messed up because it looks like the Dr. L, it looks like basically I see what to me appears to be, look at this, Lindsay. So we got a nice band here of dark blue, which looks like about minus 70 knots in toward the radar. All right, and what I didn't do, let me do this. There's the range rings. Dr. L is adding some range rings. So AHAM, I got range rings on here. So this first range ring is about 50 kilometers. So we're at least a kilometer above the surface here. So what's going on here? So Robbie, check that out. I have minus 70 inbound towards the radar, right? And then what does it do? What the heck is this? It looks like then it jumps, holy smokes, it jumps. This is, you know, if you don't process your data, at some point, it looks like it jumps to 70 out with no contours in between. It looks like, holy smokes, you've got data going from minus 70 to plus 70. No. So those who have had my remote sensing class or know something about radar, you can get aliasing, you get range aliasing basically, and velocity aliasing. And so this is all about the pulse repetition frequency. This is all about the sampling rate, all right? And so if you're not sampling enough, fast enough, ultimately, right, then you're not resolving the wind field fully. And so what happens is, everybody ever seen a moving picture of a car, a tire going on a frame per second movie? It looks like it might be going the other direction. That is a sampling rate issue. It's completely analogous to this situation. So if you set your PRF too low, you can alias. You're not sampling enough to catch the phase differential, the shifting going on from the targets toward or away from the radar. And so this is what happens. Folks have nice algorithms, so don't panic, that correct for these kind of things. But the data that I pulled is just the raw data, basically, from the server, and there have been no corrections. But it's kind of a no-brainer if you pay attention to your data set. You can clearly see these things in your data, okay? And there's no way a contour, a nicely varying contour, basically, would ultimately would just gradually go from the blue, dark blue to light blue to greens. That's not what's happening in this region. So I just wanted to bring your attention to that. Outside of that, where you're not aliasing, right? So the winds get large, you're aliasing outside of that region, folks. Outside of that region, I can show you here, you have a pretty nice variation across here. So it looks to Dr. L as I go in this direction. I go from basically along here. Again, we're going in this direction smoothly, basically, from dark blue to light blue to green, basically, essentially to gray, well behaved. Got it? So, Fallon and gang, buyer beware, as they say in Latin, caveat emptor. I don't know if that made the mug or not, but whatever. You might ask me what a muggernaut is. I don't know. Maybe it's related to an astronaut. I don't know.
All the quotes you said today pretty much are on the mug.
Awesome. I'll have to come up with some new ones, apparently. There's some missing, though. All right. So anyway, kind of neat stuff. All right. So what else do I want to say about today's stuff? I think that's not too bad. A little bit of about Doppler radar and a little bit about hurricane structure, momentum transfer, Tangelo, that came up in the Hurricane Center discussion, which is kind of nice, right? And so that's kind of cool. And I don't think I have a heck of a lot more on this one. We could go back and look at the tornado reports. I'm okay with that one if we want to do that. If anybody has other requests, That is possible as well, because I think, hold on a second, let's see if Dr. Ellis covered everything he wanted to. So that was the hurricane discussion, at least the stuff I wanted to talk about, which is kind of cool. Kind of recovered from the chaos of earlier. I did not reload the surface pressure data on. I could have. I guess if I come back to this figure again, clearly you can see north of the radar, this is the fascinating thing, right? So look at this range ring. Let's have some fun here. I will do this. So let's do this. So this guy here, this guy is 50 kilometers, right? So this guy is 100 kilometer. I don't know, the numbers didn't want to print out. This is 150 kilometers away. So as you get further away from the radar, and you're looking in this, say, this direction, right? For a second, let's do that. In that direction, you're out at 200 kilometers. Then this path, I mean, the point here being, you look at this guy, this patch of red here, this area right in here in particular, looks like about 50 knots. And clearly you're much closer to the radar. And so the winds are going to be, certainly these winds might be making it to the surface or close to it. Panor and gang and Bishop and Robbie and gang and Steph, this stuff up here clearly is not just above the surface because it's at a range ring. This range ring here is 200 kilometers from the radar. And so these are the way you kind of think of these figures, right? And so if you sort of think about that one for a second, and I went back to my figure, wherever it may be, the radar 101, right? Cancel, get out of there. Let me come back on here. So at 200 kilometers, right, we're looking at essentially all the way up here. So Dr. L's got, you know, you're almost 4 kilometers, you're 4,000 meters above the ground. And again, this is for a standard atmosphere, but it's pretty good. These contours on here are pretty good. So for the half a degree, that base tilt, that data that's far away from the radar, this stuff is really way up, right? And so this stuff's probably not making it anywhere near the ground. The center of circulation, of course, is showing up nicely with these higher winds near basically the radar. And so this stuff here basically is much lower, much closer to the ground. And so these are important things to think about, right? When you think about momentum transfer, right, and these downdrafts and the precipitation pulling in the higher velocity air down, this stuff's got a lot longer way to go. It's a lot higher off the ground, right? And the winds below it, near the ground, basically, that the precipits falling through are going to be weaker below it. These are pretty high and they're near the surface. So I don't know, a couple of things. I think I'll stop sharing because I have to be on another call at 2 o'clock, and we'll make sure.
You mean 3 o'clock?
3 o'clock, yes, that too. It's the other 2 o'clock.
He was saying it for me. He was saying it for my benefit. That's all.
It's the other 2 o'clock.
2 o'clock somewhere.
It's right.
Yeah,
Thank you. It's right.
Fun.
It's like a broken clock. Hey, this is a neat thing. I can't stop, right? This is, everybody knows Dr. Ellie can never stop. You just have to walk out, basically. So I won't take offense at that. So this is a product that we built, actually, that Brian Holman worked on, my PhD student Jeff Colvin worked on. This is a lagoon setup. This is the Indian River Lagoon, basically, which is kind of cool. It runs on forecast winds, global GFS, so you get a little kind of plume spaghetti diagram on the right here, the dates on the x-axis, and the gold circles here are what we call validated observations, and it's just a difference in the water levels, Mr. Panor and Aham and gang. It's just a difference between the water levels of Fallon from the north part of the lagoon to the south part of the lagoon, basically, down to like Sebastian Inlet, right? Based on some parameterization. So these are not observed, but they have observed winds, basically, that are used because the lagoon is pretty much a closed estuary. And if there's any changes in water level, and it's pretty shallow, the water gets pushed around in the lagoon, it's driven by the wind field. And so the cool thing here is we have the observed winds on this diagram right here. So these are the observed winds up here through the period, basically leading up to the tropical cyclone. The passage of the tropical cyclone is showing up really nicely in the data. This is not a pressure data. This is not temperature data. This is just the difference, basically, from one location to the other. The winds, folks, basically are The offending winds basically as the storm passed to our east were the onshore northeasterly flow that are showing up really nice here. And it's pushing that wall, all that water in the north part of the lagoon, sloshing it southward. And we're just taking the difference basically of the north minus the south. So the north is going down, the south is going up, so you're getting negative values. So I thought I'd share that neat little product with you guys. So if you come in here, it looks like that value down here is somewhere about, somewhere about a minus, I say about a difference of about 40 centimeters with a set down in the north part of the lagoon and a set up in the south part of the lagoon. Okay, that's almost a half a meter. So if you live on the lagoon and you're down on the side, basically where the water levels are coming up a half a meter, that can get a little scary, right? And so, all right. So we developed this product here. It runs 4 times a day based on the global forecast system. And that's enough of Dr. L's shameless plugs for today. Don't do any commercials. What can I say? All right, that's probably just more than you guys ever wanted to hear. Oh, wait, here's some more stuff. I'm out of control. So this was pulled from, this is a report from actually Melbourne, some work that Bart Hagemeyer did. He's now retired at the Melbourne office. And these were the motions and tracks of storms, basically, that produced tornadoes, basically, in the region. And I wanted to show you it's, you don't see any west to east moving, east to west moving tracks on here, do you? And so, again, if part of this is the wind field issue going on in terms of the direction of motion, basically, but it's more than that, interestingly enough, but part of that. So again, and Irma produced a heck of a lot of tornadoes, basically. And remember, this is an old picture, if we added Irma in here, she came right up this direction, right up the state, right? Moving from basically south to north across the Florida Peninsula and produced basically, excuse the term, a buttload of tornadoes basically along the east central Florida coastline. And Steph, don't ask me to quantify that, please. Okay. And Lindsay, that goes for you too. I might do it for Shiptowski though. Yeah, he's a nice guy.
You know, interestingly enough though, when Hannah hit here last weekend, we didn't see the tornadoes until Sunday, when the storm was actually over into Mexico.
So, right. So it was drifting, although that was kind of, but it was still sort of on the right side of landfall.
Right, exactly.
And the other interesting thing about your case is that, I guess let me hit stop sharing. I guess on your case, I would say it's a strange storm motion.
It really was.
Very rare does any of our coastlines get hit from the northeast. It does happen, but it's a bit strange. When you go on and you look at the number of days for tornado production, it depends, of course, how strong the cyclone is that makes landfall. If it's stronger, it can take several days for the wind field to decay. And remember, the decay is faster near the surface than it is aloft. And so what that means is you're developing wind shear as part of the decay process, because the winds stay high aloft and they decrease more rapidly. They're decreasing everywhere, but they're decreasing more rapidly where you're losing momentum at the surface. And so you're developing this wind shear profile. So a stronger storm is likely to basically have more days, Andrew, of possible tornadoes. They can go 2 or 3 days after the event. And they're not always, and there's also stability issues, right? And so you're playing games with you'd have to go back and look, but it may be that you ended up getting more surface heating the second day and more convective tape, right? I would be interesting to look at, right?
Yeah, about to take a look back, yeah.
Yeah, you probably get some fairly quick answers on that. I don't know. Anyway, I've got my Hollywood Squares back up. Any questions for Dr. L?
We have less than a minute.
A pleasure.